Hello, my name is Marloes Mul and I'm an Associate Professor of Water Resources Management at IHE Delft Institute for Water Education. Today I'm going to talk about the opportunities and limitations of the WAPOR data. Some of the key advantages of the WAPOR data are listed here. With the WAPOR soon to be a global data product, the information can be accessed for all locations on the globe. It presents a near real-time dataset with data available at decadal, meaning roughly each 10 days, time steps from 2009 to present. The data is accessible through various ways, through the WaPOR portal, API, and Google Earth Engine. The methodology used to create the WaPOR data uses the same methodology globally. It's therefore reproducible and geographically extendable. Based on various quality assessments, which will also be discussed in Unit 3.2, the quality of the data is compared to other spatial data products, but not necessarily as accurate as locally calibrated surface energy balance models, which of course require validation locally. The WaPOR data continues to be updated with provisional near real-time data produced using AC ERA 5 and ERA 5 data, which is replaced with a final product within 6 weeks using the GEOS 5 input data. As the WaPOR data is dependent on different satellites, the availability of data in the various resolutions are dependent on the data available from these satellites. In version 2, the MODIS satellite is the main source for the level 1, which produces data at 250-meter resolution. For level 3, the Landsat data is the main source, producing consistently data for the full period from 2009 to 2023. This is not the case for level 2, the 100-meter data resolution, which was developed with the PROBA-V satellite in mind, which was only launched in 2014. And the prior data was developed by resampling the 250-meter resolution data. In addition, in the last year, the level 2 data was created using the Sentinel data as the PROBA-V satellite had problems. This created some discontinuity in the data, affecting the ability to do trend analysis. All data created using the version 2 methodology will not be updated after 2023. For the version 3 data, the data will be made available from the year 2018 forward. So there will be an overlap of data available between version 2 and 3. The main source of data will be the various Sentinel satellites completed with various other satellites, which have slightly different resolutions compared to the version 2 data, with level 1 having resolution of 300 meter and the level 3 data will be made available at 20 meter resolution. Whereas the WaPOR data is provided in a specific resolution, the input data needed to produce those layers has varying resolutions, with a rough indication of the resolutions here around the equator. An example is the actual evapotranspiration input data source, which are listed here, with the key parameters available at the respective resolutions of the WaPOR data product. Various other data sources come in relatively coarse resolutions, with the climate data in 10 to 28 kilometer resolution and the precipitation data needed to estimate the interception from the CHIRPS data set at 5 kilometer resolution. Some of the static or annual data, such as the data derived from the digital innovation model and land cover, are available at different high resolutions. The solar radiation from the Meteosat second generation comes in 1 kilometer resolution, as well as the land surface temperature. As the land surface temperature is a key input into the moisture stress and relatively soil moisture, it has a strong influence on the final results. In each case, the input data has to be downscaled, and in the case of coarser data to the required resolution, which may influence specifically very heterogeneous areas and more advanced downscaling tools may be necessary. On the other hand, data may need to be upscaled or reprojected to fit the final resolution of the data, which may result in losing information. As you can see from the WaPOR portal, the WaPOR data is continuously available. However, the methodology used is based on visible and thermal bands that are affected by cloud cover. As different satellites have different overpass frequency, for instance MODIS data, the main source for level 1 has a daily frequency, PROBA-V passed by at the same area after roughly every 8 days, and Landsat after 16 days. With higher frequency data, it is more likely that there are actual observations taking place within the WaPOR's decadal time step. However, if a Landsat image for a case study is affected by cloud cover, it immediately creates a data gap of 1 month, and worse if more images are affected by clouds. This also has an effect on the quality of the different vapor level data. Users often associate the higher resolution data with better quality data. However, this data is more often created using various gap-filling approaches compared to the lower resolution data. For the version 3 data, the producers will be using data from multiple sources to overcome some of these challenges. If you are wondering about the quality of the data you are using, the WaPOR portal provides two indicators. For each map, it provides a quality layer which provides the information about the number of decades since the last valid observation. The second indicator provides a long-term assessment of the data with a percentage of good observations for the entire dataset. An example is provided here, which showed that in certain areas, especially around the coast of Africa, the percentage of good observations are less than 25%. And in a large part of the Democratic Republic of Congo, Rwanda and Burundi, the value is less than 50%. WaPOR is generated in UTM projections. This is then uploaded to the WaPOR portal using a different projection, the geographic projection. There is therefore a loss of the quality of data due to the reprojection. From the WaPOR version 3 data, this will also be available in the MGRS tiling scheme based on the UTM projections. So users can access the WaPOR data in the projection it was generated without the loss of data due to the reprojection. The WaPOR data creates the actual evapotranspiration layer by calculating transpiration, evaporation, and interception separately. The interception is calculated first, and this is dependent on the precipitation, which comes at a very low resolution of 5 kilometers. The interception does not take into consideration interception by sprinkler or center pivot irrigation. For the estimation of transpiration and evaporation, very similar equations were used, with the net radiation attributed to transpiration or evaporation using the presented equations. The main split is dependent on the leaf area index multiplied by the light extinction factor, alpha in this case. In the ET-Link model, this parameter is fixed for all land use classes at 0.6. However, as Zhang et al. Found out is that the light extinction factor for net radiation varies for different land cover classification as well as within land cover classifications, thereby affecting the split between evaporation and transpiration. The WaPOR biomass production, in absence of detailed information about the vegetation or crop type, assumes a land use efficiency of C3 crops of 2.7. For crops that have better efficiency to convert carbon into biomass, either C4 or CAM crops, the light use efficiency has to be corrected for. A crop map is therefore needed to correctly estimate the biomass production. In addition, managers are often more interested in the marketable products, also called yield, and therefore the corrected biomass production has to be converted to yield, using two additional parameters, the harvest index and moisture content of the biomass. As different factors such as stress and harvesting methods may affect these two parameters, the calculation of the yield may not be accurate. For research, more research should go into improving the estimation of the harvest index and moisture content of the crop. Finally, I would like to go into a bit more detail regarding the WaPOR data in heterogeneous areas. We already discussed briefly the implications of the different resolutions of the different input layers. Here I would like to focus on one of the resolution layers, the land surface temperature, which is used to calculate the relative soil moisture content and influences the evapotranspiration in the form of water stress. We observed that specifically in areas with high contrast, such as very wet and high evapotranspiring center pivots located in very dry areas, the ET estimation for the center pivots is relatively low. The version 3 now uses an improved thermal sharpening algorithm, and the expectation is that the results will be much better. The WaPOR level 3 high resolution will only be available in specific locations, with 300 meter vapor product available globally and 100 meter vapor product available also for Africa and the Near East. As this example for two locations in Egypt show, is that this resolution will affect the analysis and the interpretation of the result, as the field sizes and the resolution sizes are not matching up. To overcome this challenge, IHE Delft is currently testing the downscaling of WaPOR product using PyDMS. As you can see from these two examples, the results show excellent spatial pattern, matching the natural color image. Some caution has to be considered as the source of the data stems from the lower resolution data, and the team at IHE is still in the process of validating some of these results. One of the key input layers to the ET-look model is the land cover classification. For version 3, the base layer is the Copernicus land cover classification for the year 2015. The yearly data available through the portal has an additional yearly varying split of the cropland class into irrigated and rain-fed crops using a water deficit index. Because this data is available annually, land cover classification that changes during the year, such as seasonal flooding, are not taken into account. The WaPOR version 3 will not include a land cover classification layer, which will be available through the World Cereal portal, including the irrigation versus rain-fed split. This will now be based on the ESA World Cover Map. However, it's good to note that the land cover classification affects the WaPOR data, as the ET-look model considered several land cover related parameters, and a misclassification may influence the data. To summarize this presentation, I'm listing a few key challenges and limitations of the WaPOR data. And these challenges and those I discussed in the previous slides are not specific to WaPOR, but do apply to the majority of remote sensing derived data products. In order to be able to interpret the data and use effectively in decision making, the user needs a good understanding of the domains the data is to be applied to. Further capacity development of the use of WaPOR data is required. Also, with more and readily available data, the biggest challenge is translating this data into information. Further limitations are the right spatial and temporal resolution for specific applications. Some of the sensors may not continue to collect data, and alternatives need to be found. Switching these sensors over time may affect the quality and consistency of the time series. And finally, a lack of a dynamic land cover map has various implications on the quality of the data. Thank you for your attention.